Okay, hi everyone. So we've been working on logarithms, and our slogan for logarithms has been logs solve for exponents. Log solve for exponents. So we came up with stuff like 2 to the x power is equal to 8. And we know what this is. We know that 8 is really 2 times 2 times 2, right? Which is 2 cubed. So if I write them next to each other, 2 to the x is equal to 2 cubed. Well, yes, that means x has to be 3. Right? That's like a classic way of doing it. Um, but using logs, we can spin this around. And we say, no, we can solve this using logs. So log solve for exponent. And we have an identity where we circle of logs, but kind of backwards. We log with the base of 2 of the answer. 8 is equal to the exponent. So we have our base. I call this my answer. And this is our exponent. And you can see in this form that logs literally solve for exponents. The x is the exponent of my answer, right? That's what the log is. So if we could use this on some type of calculator, that would definitely help us solve it. And we did work on this on calculators. We said, if I could write this on my calculator, and we had something called a change of base, or I could write this as log of 8 divided by log of 3, no, log of 2, I'm sorry. If you type this exactly in the calculator, you end up with the answer 3. It does all the work for me. And of course, for these simple problems, it's a great way for us to remind ourselves how to use logs. In case you forget, maybe you're taking the SAT and you totally forgot how to use a log, come up with something that you know the answer to, 3. And maybe you can play with your calculator to figure out what the answer, like how to spin that around. Now, if you guys have a nice fancy calculator, you could just have typed this. Calculators that are super fancy are like $10 these days. And you have a little button that says log base with the open end here. Sometimes you might have log, oops, let's say log like A and then B, or they'll use X and Y, depending on the variable letters. So that's something that we worked on before, just plugging logs in there on the calculator. So how can I actually use logs to apply for harder problems? Okay, so how do I use logs to solve for harder problems here? Now, if I give you a problem that says, oh, someone's coming in here. Okay. So what if I write this? If I write, so today we're going to work on how to use logs algebraically. How to use logs to solve. Now we're going to solve our problem that we just did right now using our logs, but not using an identity today. We're going to say, what if I had 2 to the x power is equal to 8? Now we're going to use an algebraic process like what we've done in all our classes up to now. And we're going to use logs like a multiplication, like a division, like a subtraction. We're going to use it in that manner. And here's what we're going to do. In order to solve for x, would you guys agree that x is in the exponent? And if I have something in the exponent, I should be thinking logs. I need logs to beat down that 2, so the x is going to drop, right? You have an apple in the tree. Are you going to, I mean, you can't hit the tree, the apple's going to fall. But you got to get something to reach up there, right? And usually it's a big stick. It's a type of log. So what we're going to do, we're going to write log to both sides. So would this still be equal? If I do a process to one side and I would do a process to the other, would this still be equal? And in algebra for us, if I do something on one side, I can do it to the other. See, we're pretty much applying logs. We're like multiplying log. But no, it's not really multiplying log. It's actually we're taking the log of. Now there's a trick about logs we talked about. Logs bring down exponents. And we're gonna take this x here, and where does the x go? All the exponents of logs go to the front. And we end up with x log of 2 is equal to log of 8. And see, that is the process of what logs do for me. They take the exponent and they bring them to the front. No matter what the exponent is, it brings that exponent to the front. And then we have x times log of 2. Now, log of 2 is just a decimal number, whatever that decimal number is. So since it's a decimal number, I can just do an operation to it. And the operation I'm going to do is divide. Is it okay for me to divide on both sides? Yeah, definitely. So x is equal to log 8 over log 2. And this is the exact same answer we had up here, log 8 divided by log 2. And that's our calculated answer, 3. Okay, so the process is the new process that we learned is just writing logs to both sides. And when I have a log on both sides, I'm going to end up taking the exponent and bring it to the front. And then we can treat it like any other log. Right, so let's give ourselves a harder question, some one that we might not be able to solve. If I say 5 to the x power is equal to 10. Now, you might see Mr. Co's answers too. 5 times 2 is 10, Mr. Co. Well, nice try. This is exponent. So 5 to the what power, 5 to the what power is 10. Now, just to show you that this is not going to be a nice, easy number, this is going to be a decimal. What's 5 to the 1 power and 5 squared? 5 to the 1 power is 5. 5 squared is 25. And isn't 10 kind of in between both those numbers? So it's 5 to the 1 point something. 5 to the 1 point something, some decimal number. 5 to the decimal number. So what would that decimal number be? Like, would you automatically know what it is? Do you guys know all your exponents of 5, especially all the decimal values? No, impossible, right? So this is where our calculator comes into play. But before that, we're going to set up using our logs. We could use our identity, sure. But let's go ahead and use our log to both sides. And let's try this method. This is algebraic method, not memorizing identities. This is just log both sides. And this is our technique. I want to get that apple up in the tree. I need to go get myself a stick because logs bring down exponents. And when I do my log to both sides, check that out. That's going to move to the front. X log of 5 is equal to log of 10. Now, log of 5, ooh, what is that? I don't know what it is. It's a decimal number. And what's x times a number? We can divide that number away to both sides. X is equal to log of 10 over log of 5. Okay, now I don't know what that is. Let's see if I can take a calculator here. Let's use this guy here. This is a new calculator I got. So hopefully this works okay. We're going to do our problem, 10 log. Oh, you can't even see it. It doesn't even shrink. Oh, darn it. I was hoping that would work on split screen, but it didn't. Let's use another one. This is more of a scientific calculator, okay? Oops. Adds. Okay, here we go. What we're going to look at is 10 log. Let's see how this calculator works. We're going to see 10 log. Oh, this is, if I write 10 log, take a look at what it looks like, because you might not be sure how your calculator works. As you can see, this is in the wrong order. So I'm going to write log of 10 instead. Close my parentheses, divided by log of 5. Enter. We end up with the value of 1.430. X is equal to approximately 1.430.
At Chewy, we know that.
Adds. I need to find another calculator. Now, would that be true? So far, it fits our criteria. It has to be between 1 and 2, because 5 to the 1 is 5. 5 squared is 25. So 5 to the 1.430, would that be 10? 5 exponent of 1.430. Let's see if we can figure this out. 5 caret. This caret is my little button in the corner here. That caret here is my exponent. And 1.430, this is approximately 9.989, which is our rounded value of 10. Okay, so we can say, hey, that is approximately 10 because of round off error. Great, perfect. So we were able to solve it using logs. Could I have done it using identity? Sure. That is totally okay also. Okay. So let's look at some other problems. What if I say 5 to the x plus 3, okay, is equal to, let's say 25 here, okay? Now you could probably figure out in this way what we were talking about before, since I can make 5 into 25, here's our classic way, 5x plus 3 is equal to 5 squared. And then you can set the exponents equal to each other. We can do that. And then x minus 3 minus 3, x is equal to -1. Totally possible. Okay. And if we can do that, great. But let's say if you are totally clueless and you have no clue what's going on, whenever I see a variable in exponent, I'm just going to log both sides. So let's do this using our algebraic way of logging it. Log 5 to the x plus 3 is equal to log of 25. Okay, 5 to x plus 3 equals log of 25. So what does the log do to the exponent? Logs bring down the gods. That goes to the front. Parentheses of x plus 3 is equal to log, darn it, I'm sorry, not cosine. Log of 5, right? We say the exponent goes to the front. We just copy to the front. I'm going to write parentheses to make sure it's not, if I don't write the parentheses, it'll look like this, x plus 3 log of 5. Now, does that mean I'm multiplying log by both x and 3? No, this means the 3 goes to the log only, which isn't what we want. That's not what we want, right? So we have to put a parentheses. So please don't be lazy about that. We have to write the parentheses here. Is equal to log of 25. Now, what do we say about this log of 5? Log of 5 is just a decimal number, just a number. So we're going to just move it over. X plus 3 is equal to log of 25 over log of 5. Now, if I don't know what the value is, I can break out my calculator. Let's go break out the calculator again. Okay, we have 100 seconds before our next ad. So I'm going to type log of 25 divided by log of 5. And you end up with the number 2. Okay, perfect. The number 2. This is equal to 2. X plus 3 is equal to 2. Oh my goodness, that's exactly what we wrote up here. So if we think smarter than harder, definitely. Minus 3 to both sides. X is equal to -1, like our previous answer said. Now, just a side note here, if I write log of 25 over log of 5, remember this is change of base? Change of base. This we can rewrite this as one log. Log of what? Log, what's my new base? Log base 5 of 25. What do logs solve for? Logs solve for exponents. 5 to what exponent gives you 25? The circle of logs. 5 squared is 25. And that's how they end up with 2 here. Okay, sorry, that's how they end up with 2 here also. So if you want to go to logs that way. Okay, so are logs helpful? Yeah, they help us solve for anything that has an exponent. If it has an exponent, we can solve it using logs. Let's look at another case scenario. If I write e to the x equals to 10, something like this, e to x equals to 10. We need a special log for this e. Oh, can you console by log? Okay, question is, can I divide logs? Let's say log 3 divided by log 6. No, you cannot divide logs by canceling this way. That does not work. Why? Because this is not, okay, rewriting it. This is not 3 times x. This is not 6 times x. In this case, yes, we could divide out. This is log of 3, log of 6. If I want to write it a different way, remember writing stuff in functions, we can't just cancel out the f. You would have to answer the f first and then deal with the results. Okay, so this isn't f times, this is f of. That's why. Another way of looking at this, imagine if I wrote square root of 3 over square root of 6. Can you just divide the square roots? Oh, this is just 3 over 6. It's the same process. It's the square root of 3, the square root of 6, the log of 5, the log of 6. Good question. So that's why we can't just divide it. We have a special rule for this. This is actually change of base. That's a change of base, which isn't division. So logs have its own language. And that's why you have to remember all our little special skills for logs. If I'm adding logs, log of 3 plus log of 5, this is really log of 3 times 5. This is log of 15. Because they have their own special language. If I'm subtracting logs, log of 3 minus log of 5, this is really log of 3 divided by 5. I'm actually dividing on the inside. So logs have their own special language. So we can't just divide. Same thing, you can't factor them out. You can't say, oh, this is the log of 3 plus 5, which is not the same answer at all. Because we're not multiplying log, this is log of, it's a function. Good question though. Okay, so let's take this e to the x equals to 10. Now, how do we deal with e? We have a special log here. So we're going to use natural log to both sides. In this case, we have natural log. Now, we can look at the process by which logs bring out exponents. Bring this item to the front. X is equal to natural log of e equals to natural log of 10. If you remember, these are inverses of each other. This is really log base e of e. And what's log base e of e? How many e's does it take you back to get back to e? Circle of logs. E to the 1 power is e. So we write it as x to the 1. Or just cancel them out. These would just cancel out. Gone. That's just 1. Okay. Natural log of e, which is just 1. Circle of logs. Okay. All right, so let's go ahead and go the other way. Let's have a log problem and work backwards to solve for that log. So let's go spin it around. What if I give you a log? Log of x is equal, okay, log that's a log base of 2 of x equals to 3. How would I solve this problem? Well, if you can see, the x is inside the log, it's stuck. So the way in algebra, we want to get rid of this somehow. That's our algebraic approach. Get rid of the log base 2 and we're good. Now we have our fast way of solving this, and that's circle of logs. Our identity will take 2 to the cube power is equal to x. 2 to the cube power is equal to x. Why? Because don't logs solve for exponents? So that 3 is actually an exponent. That's actually an exponent. That's an exponent. So I write an exponent position with the base of 2. And 2 times 2 times 2, 2 times 2 times 2 is 8. And our answer is 8. Perfect. Log base 2 of 8 is 3. That's a direct answer here. But that's you memorizing the identity. Let's talk about the algebraic approach today. How can I solve this with the algebraic approach? And what can I do to both sides to clean this up? So let's go ahead and rewrite the problem. Log base 2 of x is equal to 3. Now, here is the algebraic approach. Let me ask you, what does 3 represent? Would you be okay that 3 represents the exponent? So let's raise it back to its prominence. Let's put it back up on this pedestal with the 2 as a base. And this is the algebraic approach. If I raise it up to an exponent, well, log base 2 of x is an exponent, 3 is an exponent, let's write them as exponents. And here's what happens. When you write this exact base, 2 and 2, this cancels out. And you're left with x by itself. And that's exactly the same as our identity here. Well, let me do this a couple times for you. You might think, no way, that's kind of, seems like a cheat, but it's not. So I'm gonna go ahead and give you 3 different problems and we're gonna do the exact same thing 3 times. Okay, log base 5 of w is equal to 2. Log base 4 of x is equal to 5. And log base 7 of x plus 2 inside is equal to 3. Okay. We have logs, we have our variables stuck inside. Free me, let me go, I'm innocent. Okay, let me out. So how do we get them out? Well, what's the base? The base is 5. So I'm going to write 5 to both sides. Look at our second problem. Before we finish the first problem, look at the second problem. Oh, yeah. Yeah, you do that. Okay. Okay, next one, my base is what? 4. So this 5 here is an exponent. So I'm going to make it back to an exponent with a base of 4. The last one, what's my base? Hopefully you see it's 7. Now, the next part is canceling. What happens to the 5 and the log 5? Cancel out. 4 log 4, cancel out. 7 log 7. See this inverse operation here of making stuff back into an exponent. That's that inverse operation that solves it, cleans it up. Now, on your work, when I see your work, when you're taking a test like this, I need to see work like this. I need to see you writing it out algebraically. Or you can give me the identity, but I need you to show me with an arrow or something. Hey, I'm using the identity, write out. I use the identity. Or write this work here. So W is equal to 5 squared. X is equal to 4 to the 5th. And X plus 2 is equal to 7 cubed. In this last problem here, I still have to solve it. I get rid of 2 to both sides. X is equal to 7 cubed, which I don't know what it is, minus 2, right? So the goal is to get rid of that log somehow. What if I'm not given a number? Sorry, excuse me. We had a couple special logs here. What if I wrote natural log of X is equal to 2? What if I wrote log of X is equal to 3? These are both special logs for us. Do you guys remember what type of base we have for natural log? What type of base we have for a common log here on the right? Do you remember? Oops. Do you remember? I clicked it too fast. I'll try and get rid of these Outlook notifications. Okay, so if you remember natural log, the base we talked about just literally like maybe 4 minutes ago is e to both sides. And don't be afraid to write that because 2 was an exponent. So that's bring it back to its prominence. Bring the king back to the throne. What is my base for log, common log? It's an invisible 10. If you remember, it's actually an invisible 10 here. Common log is invisible 10. So if I write 10 to both sides, now these cancel out. The logs base 10 and 10 cancel out. And we're left with x is equal to e squared and x is equal to 10 cubed. Hopefully I'm demonstrating in a way that kind of makes sense. We're repeating these same skills. It's the same skill for all these types of problems. Okay, so what if it's not log by itself? What if there's a bunch of stuff going on? What if I write log base 3 of x minus 6 is equal to 2? Okay. Yeah, sure. Okay. So what happens here? Well, please take note. Please take note. Is the 6 inside the log or not? Is the 6 inside the log? Because if it was, I would have purposely put a parentheses. I didn't forget the parentheses. There is no parentheses. So it turns out this is a problem with a 6 attached to it. So the way we would solve for this is order of operations. I'm going to get rid of that 6 first. I'm going to plus 6 to both sides. Then we have log base 3 of x is equal to 4. Oh, oops, sorry. In this case, 8. 6 plus 2 is 8. Now we're back to a regular log problem. So how do we get rid of the word log base 3? What's the base? 8, is 8 just a regular 8? 8's an exponent, right? Log solve for exponent, 8 is an exponent. So we're going to give each other a 3 to both sides. Those cancel out. X is equal to 3 to the 8th power now. Hey, so sometimes like in algebra, you have to clean up the problem before you can actually do your log skill, that new skill that we're learning. Sometimes we have to clean up our problem first. Okay. Maybe we have to clean up that problem. Okay. Let's see. All right. So let's look at one more thing here. Do these problems get that much harder? No, not the activity of the log itself. The numbers sometimes get a little more difficult because the decimals are kind of big. So let's look at another type of problem. What if I put a number in front? What if I say 3 log base 2 of x is equal to 9, let's say, okay? Now, if you notice, I have a 3 in the front. So I can't do this yet, okay? You cannot do this yet because of that 3 in the front. So we have to clean up first. Let's get rid of the 3. Divide the 3 first, both sides. Now we're left with log base 2 of x is equal to 9 divided by 3 is 3. And then we're going to take 2 to both sides. X is equal to, bam, 2 cubed. I would never have guessed this answer. Nope, not me. But let's see if this is the right answer. 2 cubed is 8. Would this have been true? 3 log base 2 of 8, would that somehow equal to 9? How does this become 9? In what world does this become 9? Well, let's remind ourselves. Let's solve for this log first. 2 to what exponent is 9? Circle of logs, because logs solve for exponents. 2 to what exponent is 9? Is 8? 2 to what exponent is 8? 2 times 2 is 4, times 2 is, 3. 2 cubed. So this is actually 3. And 3 times 3 is 9. Oh my goodness, I would never have guessed that. What if I have multiple logs? Oh no, Mr. Ko. Why would you do that to us? What if I write log of x minus log of 6, but let's give them both a base of 4. Oh no, Mr. Ko, what are you doing? What are you doing? Log base 4 of x minus log base 4 of 6. Can I just write 4 to both sides? You can't do that. The way we have to use logs is we can only do the trick if there's only one log. We have to combine these logs somehow. Are we able to combine these 2 logs on the left? A log minus a log. Do you remember what's the rule when a log minus a log? If we are subtracting logs on the outside, we are dividing logs on the inside. Do you guys remember? I can rewrite this as a division on the inside. Well, now that we have one log, we can do the rest of our work, which is, how do I get rid of this log base 4? Remember, 2 is an exponent. Let's bring it back to its prominence. Let's give it a 4 to both sides. See you later. We are x over 6 is equal to 4 squared. 4 times 4 is 16. Almost done. Let's multiply the 6 to get rid of the 6. See, this is straight algebra work now, right? And this is why it's algebra 2. It is harder. It takes a lot more steps. It takes a lot more thinking involved, a lot more planning. Our solving for x might involve a couple extra steps here just to set it up before we can actually use that log rule. And 6 times 10 is 60. 6 times 6 is 36. That's 96. 60 plus 36 is 96. That's our answer. Excuse me. Now, you might not believe me, but log base 4 of 96, which I would never have guessed, minus log base 4 of 6, this is somehow going to equal to 2. Somehow. Let's try this on my calculator. So if I don't see this work here, these are just magical answers. But let's go ahead and type it. Let's see if I have a special base here. Do I have a special base here on this fancy calculator here? I don't, so I'm going to have to type it the long way. So log 96 divided by log of 4, okay, minus log of 6 divided by log of 4 equals, oh my gosh, it became 2. It became 2, right? Excellent. The answer on my calculator said 2. We must believe it, right? Okay. So these questions can get a little tricky, but because we're using all the rules that we learned before about logs, let's give ourselves another problem, and we'll just do one more. Log base 6 of r plus log base 6 of 6 is equal to 1. Okay. Well, here's a trick. Do you know what the log of base 6 of 6 is right now? That's just going to become 1, right? 6 to the 1 power is 6. So we could do that. But let's not do it. Let's do it our way that we've been practicing. Log base 6, bring them together. If I'm adding logs, I'm multiplying logs. Okay, if I'm adding logs, I'm multiplying logs. Right, because r plus 6 is r times 6, 6r. Okay, how do I get rid of the log? We have a base of 6 to both sides. 6r is equal to 6 to the 1 power 6. Let's divide both sides by 6. R is equal to 1. And that's what we were expecting, r is equal to 1. Okay. All right. Do logs get more tricky? They can. Now here is one more for you guys. What if I see logs on both sides? Log of x is equal to log of 6. I want you to see this is very similar to when I was writing this. 2 to the x is equal to 2 cubed. Couldn't you just say x is equal to 3 and x is equal to 6 here? Yeah, x is equal to 6. Right? That's what we're expecting. In order for them to be the same, the stuff inside has to be the same. You got a strawberry filled donut. I want the same thing. I want that strawberry filled donut too. They have to be the same filling. But just FYI, here's the algebraic approach. What is the base for log on both of these logs? The base is 10. Okay, and these cancel out, leaving you the inside. Let me do this again with another. Log base 3 of x is equal to log base 3 of 6. Hey, look, what's the base? Well, if I put 3 to both sides, that's our inverse operation. X is equal to 6. If they're not the same, then we're screwed. We got to do something else. If they're not the same, we're screwed and we got to do something else. We got to rewrite the problem. Okay. What if I write log of x squared plus x is equal to log of negative 6. Okay. Now this is a tricky one. Oh no, sorry, positive 6, positive 6, positive 6, positive 6. Sorry, positive 6. Tricky one. Well, this problem is totally impossible for me. Let's go ahead and do base 10 to both sides, clean it up, and we're just re-looking at the inside part. I'm gonna go ahead and move it around, subtract 6, because I can always solve x squared by making it equal to 0. Now, is this factorable? Two numbers that multiply 6, that's subtract that to become 1. Two numbers that multiply 6 become 1, x. Now, if you notice that we are using everything we've learned in math so far from Algebra 1, solving inverse operations, everything we've been doing from square one, x is equal to negative 3 and x is equal to 2. These are my two possible answers. Okay. Now, the question is, will both of these be correct? Now, whenever you have more than one, whenever you have a log answer, you always want to double check because we cannot take a log of a negative number. This is a no-no. Okay, we can't take logs of negatives because exponents won't leave you to negatives, so we don't take log of negatives. So you just want to double check. If I plug in 2 here, 2 squared plus 2, will that be negative? Negative 3 squared minus 3, will that be negative? In both of these cases, no, they would both be positive. This would be 6, right? So they're both going to be positive here. So we have no fear of that. But sometimes, and this could be an SAT question where one of them may be negative, and that is not an answer. That is not a possibility. Okay.